we're gonna break the word down. All right, so we're gonna start off with tensegrity. Tensegrity, breaking it down to tension integrity. It was coined by Buckminster Fuller, who was an architect. It was in 1955 that he started building geodesic domes, which I don't know if you've ever seen them, but it's basically triangles where nothing is really touching each other. It's kind of like a canvas, and you have struts. So these wooden pieces are compressive struts. Notice how, in this case, none of them are touching each other. So this structure is maintaining itself in space. We have the wooden rods as compression struts. We have the rubber bands being our tensional bands, which in a second we're going to relate how this connects into the body, into biotensegrity. So Buckminster Fuller, an architect, started exploring structures such as these tensegrity-based structures after World War II because he was able to do more and build more with less materials and with cheaper materials. So if you think about a building, you got to stack each brick, you have to put all of these cross beams on here. Everything is touching each other. It's all like adhesive together. It's kind of a mess and it's expensive. So what he was doing is, after the war, he wanted to build things that were cheaper, that he could use less material, and that would maintain themselves in gravity. Has anyone seen a geodesic dome? Do you know what I mean when I say that? It's fine. If not, we'll go over it later. So anyway, tension integrity, okay, tensegrity. How does this apply to a human? How does this apply to chiropractic and how we analyze the body through a chiropractic analysis and adjustment, and how does it affect your overall health and expression? This is a beautiful example of the body, of the cell, and we can look at this from a macro lens as well as a micro lens. So we'll start off big. Biotensegrity simply meaning biology, so applying a tensegrity model to a biological life form, in this case, obviously, the human body. So we can start off looking at the whole, where instead of just being compressive struts, which these wooden sticks are, in the body, these are going to be our bones. Okay, no bones in the body are touching each other. There's always spaces between them, whether it's a synovial capsule, whether it's fluid, or whether it's just a joint space. Nothing is touching and rubbing against each other, because that would be inefficient and you'd wear down the bone really fast. So what the body does is it floats itself. Right, our body is whatever percentage of water it is. It's a lot. We're mostly water. Our body is mostly floating, which is why if you just wiggle yourself, you can feel your organs moving. Everything is moving and floating, as well as your bones and as well as your joints. So in the body, these wooden struts are going to be our bones. All of the ligaments, fascia, tendons, extracellular, intracellular matrix are going to be holding it together within these rubber bands. So as we can see, just like the body, none of these surfaces are ever touching. However I distort this model, you'll never have the sides touch. So whether I'm compressing it and smushing it, what happens when I let go of it? It bounces back. Whether you're tensioning it, what happens when you let go of it? It bounces back. So again, tensegrity, tension integrity, this model is holding itself up. It's maintaining itself through compression and tension. So what we can do is apply that through a chiropractic lens when we're analyzing the body, finding areas of hypertone, hypertonicity, finding areas where there's too much tension, too much compression, and then balancing that state out. So we call that the ideal state of tension. What happens if it's not ideal? Well, that's where we're going to have kick-ups of compression and tension. Again, chiropractic founded on tone. Tension is a tone, so hypertone, hypertonicity, or lack thereof, right? Hypotonicity. And then we also have compression, which really is it's all an altered tone. It's all aberrant information. It's all distorting the way the body is supposed to be communicating and expressing. So this structure in particular, where's Jalen, is an icosahedron. Icosa, 20 sides. Icosahedron. You're close. And this is said to be one of the more efficient structures in nature because it's spherical in nature. It kind of looks like a sphere. Most of the cells in our body are spheres. Our red blood cells are spheres. Most of our cells are circular, and they're also filled with fluid. As we said before, the same way that this structure is able to be under tension, compression, and torsion, and then not get too distorted where it's damaging everything inside of it, the same way, if you've ever seen the diagram where the red blood cells are going through the veins, and the veins are constricting and dilating, and the circular, the spherical red blood cells are able to morph and change without bursting, without lysing and causing a bunch of issues. This is a very efficient structure. So what happens when there is too much tension or too much compression in the body? What happens when this structure starts to get stuck in these patterns, right? A state of dis-ease, which is what we're looking for as chiropractors. How does that lead to a state of disease in the body where we're having ongoing perpetuations of altered gene expression, altered proliferation and growth of cells. What happens is under a state of chronic tension, which is going to palpate as a hypertone, a stretched area or an active muscle that's trying to pull whatever it's holding onto back together. We can start superficially. We can start with the skin and the muscle and palpating over the body and the spinous process and the tension. We can do that, but we can also take it much deeper into a fascial level and then eventually into a cellular level. So what happens is there's connections between the bones, the tendons, the ligaments, all wrapped in fascia. The entire body is wrapped in fascia that is able to, its main job really is to maintain the structure of the body. It's, if you've seen it, it's like a web. It is a tensegrity based structure. It provides tension, it provides compression, and it communicates back to the brain where if there's a compression here, the fascia is communicating back to the brain what's going on in this area, and then it's changing the tissues around it. At the cellular level, we have something called integrins, which are super cool protein. If you're in freaking cell phys, Brayden, you just took that, you know about it. Integrins are reaching into the extracellular matrix, so the fluid that the cells are floating in. They're reaching out here. They're transmembrane proteins. So they're reaching out and grabbing onto glycoproteins that exist in the fluid. Okay, again, it's all floating. This is now going to be a cell. So picture any cell you want, doesn't matter. This is a cell and I'm an integrin. I'm reaching out into the extracellular matrix. I'm grabbing onto glycoproteins. I'm also monitoring with this arm what's going on in the matrix. Is it dynamic? Is it floating? Is there tension and compression being in here? Is there a lack of fluid? Is there a lack of viscosity? My other arm is connecting into intracellularly. So I'm now inside of the cell. And this one is connecting to the cytoskeleton that exists within the cell. Now, why is that important? The integrin is communicating to the cell what's going on in its environment. So what exists within the cell? Cytoplasm, nucleus. What's in the nucleus? The what? Mitochondria. DNA. There's DNA that's in the nucleus of the cell. So we have the integrin that's floating in the matrix, okay, extracellular matrix. We have the cell that's floating in the extracellular matrix, and then we have the contents within the cell that are also floating. So the integrin, again, is communicating to the cell about its environment on the outside. What happens is if I'm grabbing onto cytoskeletons within this cell, and there's an area of hypertonicity or of tension in this case, so think of flattening, pulling, activation, I'm communicating directly to the cell's nucleus that's going to change the expression of the genes within this cell. So this is where we're getting into epigenetics, or like how the expression of genes is going to change based on its environment. So what happens in this case when there's too much tension, when I'm being pulled too far as an integrin, is I'm going to communicate now within intracellularly into the cell, and the genetic code is now going to change, and it's going to signal apoptosis. So if there's too much tension, this cell is going to die. Why? Do we want to create new cells in a state of disease? Do we want to create new tissue and continue to proliferate in a state of massive tension being pulled? Obviously not. So this state of dis-ease is then going to lead to a state of actual disease, where now we're having repeated patterns of sickness and dysfunction that we label as a certain disease. Interestingly, I think this one is actually even cooler. That's the case of tension. In a case of compression, okay, where the integrin is actually being smushed and it's communicating that the environment that the cell is floating in the fluid, is being hypercompressed, is going to communicate to the gene to rapidly increase proliferation in a damaged state. So this is how, when we have areas that are hypercompressed, whether we're, say we're slouched forward and we have this compression on the anterior part of our body, we're also going to have tension on the outside, on the backside of the body, because the body's balancing between the two states of tension and compression. So when there's too much compression, now we're going to have uncontrolled proliferation, which we call what? Cancer. So these are some of the ways that we can start superficially when we're reading the body through the lens of biotensegrity and noticing where the body is holding tension and compression and where it's not adapting any longer. That continues to trickle down. The layers keep connecting and grabbing and reaching out further down into the cellular level, where there's actually an attachment to the nucleus, which, if you think about it, if you're distorting a nucleus and there's genetic content and DNA inside of there, you're going to change the way the cell expresses naturally. So let's get you face down real quick. So how does this apply to chiropractic? Like how can we do a prone analysis or an analysis anywhere in the body using BioTensegrity? Everything in the body is connected. So if you could picture this again, now we're going macro. So now this is the body as a whole. So we're not cell anymore. Any part of this that I pull on, whether it's the rubber band or the wooden compressive strut, the entire structure is going to distort. The exact same thing happens in the body. Nice. So when we're connecting, we're going to be doing a prone analysis right now. Can you just turn that a little bit? You can just connecting with the body now instead of trying to find like an intersegmental area where there's just one specific part that is rotated, whether it's an ASRP atlas, whether it's a shift in the pelvis, whether it's a T3 subluxation. Instead of just looking for how can we correct this one individual part, now we're thinking globally. How is the entire global system impacted? How can we find a state of ideal tension within the body so that there aren't areas of compression and tension that are going unmanaged? Because how are you going to adapt to an area that is hypertense that's pulling apart? We know what's happening within here. And we know that, yes, the neural tissue is also going to be stretching and compressing. So like contemporary models of subluxation really are saying that it's not pressure on the nerve. It's actually neural tension. It's tension being placed on the nerves that are distorting the messages from the DNA all the way up through into the bigger cells and then back up into the brain. So what we're trying to do with the body is find areas of tension, notice areas of tension and compression, and then find where are the windows into the system that we're able to access and then adjust through those spaces. So prone analysis using a BioTensegrity based model. We are always going to start with the calves. So we can come here, noticing tonicity of the calves. Really the easiest one to find at first is fullness or compression, or we're going to say hypertonicity in general. So there's typically going to be one calf that is more like flaccid or hypotonic. You could call it, for Danny, this right side is a lot more loose than the left side. When we come down, we're going to check into the Achilles. Why did we check to the Achilles? This is all a fascial chain. The whole thing is connected. So our superficial back line starts back underneath the toes, into the plantar fascia, into the Achilles, up through all of the calf muscles, popliteus, up through sacrotuberous ligament, erector spinae, ligamentum nuchae, and then it wraps all the way around to the front part of the epicranium fascia. So we can feel. You have a question? What are you looking for? So we're feeling. So the reason why we can do it was as such, because this whole chain is connected. So when we're prone, there's a lot of different chains we can use. Easiest one is superficial backline, which is why when we're doing a tensional check, this is a tensional check. When I'm pulling on the Achilles, I'm providing tension to the system, and it's going to rebound, and it's going to compress. If we have a SI joint dysfunction, whether it's a PI ilium, an AS ilium, a PIIN, doesn't matter what it is right now. If we're having dysfunction or distortion within that joint, it's going to be a compressed state. There's not really tensional, especially for the pelvis. It's going to be a compressed joint and distortion, either more posterior in the joint or more anterior in the joint. How are we going to feel that? Okay, well, if it's compressed here and we have this model, okay, and it's smushed, this isn't going to want to get tensioned. Now, what it needs is tension so we can balance it into an ideal state, but it's not going to want to release tensionally. So what we can feel as we're pulling into the Achilles is, does one leg fight you compared to the other one? So what do we have? We checked off, we have increased tonicity of the left calf. I'm going to come down. We have increased tonicity and a circular tight band of the Achilles. You can even see how much it's actually thinner than the right one. The right one is more flat. This one is like literally about half the size because it's taut. And so as we're providing tension to it, we're also going to notice that this side doesn't want to unload. There's almost no movement coming through here. The heel won't even really budge. Compared to this one, I can traction this all the way up through his occiput. His whole head will move. This side I have to like really pull, and it feels laggy. I can feel it lagging all the way up through the leg and stopping somewhere around that pelvis. So what does that tell us? Right now, this is left SI joint all day for me. So I already pretty much know from here, feel the calves, and I give a flick. I already pretty much know that there's something going on the left side. So I can just skip that, come through the left side. We can continue this palpation through the entire body, through the back part of the chain, feeling muscular tone throughout the body there. But for now, we're going to stick to the SI joint. I'm gonna come to the other side just for demonstration purposes. So if we're feeling that there's probably something going on in this SI joint, I'm also going to pay attention to what's happening to the things that are connecting into the pelvis and the lumbars in this area. So biggest one is going to be QL. QL is going to be a little bit closer to the spine. It's going to connect through every single transverse process of L1 through L5. The entire lumbar spine is connected to the QL, which is then going to attach to the ilium. If we have compression of the ilium, which is pretty common, a pretty common thing to find, what is that going to do? Well, PI typically leads to what? Short leg, we say, right? Why? Could it be that the ilium has rotated more posteriorly, is more distorted posteriorly, and then is thus hiking the greater trochanter up? Yeah. Could it also be that we have a shortened QL, a compressed QL, that's now compensating throughout the rest of the chain, pulling that leg short, which we didn't even check, actually. So we check length, we're about, it's not that bad. It's probably about 1/4 of an inch, maybe 1/8 of an inch a little shorter on this side. We could probably play around and put a little bit of tension into this QL and see that leg start to even out. So again, we're just noticing, like, there's not an adjustment for the QL, but this is another thing that now I can check. Like, it's not just, oh, there's tonicity here, cool. Everything we have right now is like left-sided, and it's all in here. Now again, it's access points, it's all connected. So is the QL attaching to a specific lumbar vertebra, a transverse process? And is that why? Is it a rotated lumbar that's causing spasm of the QL, that's then causing distortion of the left ilium, which is then pulling the leg short? Maybe. So we just fucking check. Put your hand over the lumbar. I like to use 2 fingers on each side and kind of feed in. Is there an area? What it's going to palpate as is there's going to be one lumbar right next to the spinous where you're going to feel a big bunching of tissue, and it's probably going to be right next to it, and it's only going to be on one vertebra. So for Danny, there's not really that much here. With him, I think it's a little bit more TL, junction and rib cage, as well as ilium on this side. And so you can feed in, how does this change? I can bring the ilium more P to A. So if we're stuck here, if we want to bring it more this way, as I do, does that, as soon as I feed into the ilium here, the QL completely relaxes, when this is now completely neutral, aka ideal state of tension. So this is how we can check, like, is it an ilium, is it the sacrum, or is it a lumbar? This is how we can check. It's called biotuning. So I'm feeding in to the direction of correction into the joint. And as I do, I'm feeling that this whole left QL is just melting. So now we're in ideal state of tension. So for this, I would adjust left ilium in a PI fashion, going P to A, finding wherever the restriction is most pronounced in that joint. Does that make sense? And that might be like even complex. What I want us to do is just like notice. We'll have someone go face down. Notice really with the calves. This is like, it's such a freaking dead giveaway most of the time. If like, and by the way, the indicators don't always match up perfectly. Most times they're not going to. You're gonna have things that don't really make sense, and that's why you have to trust your hands and what you feel more than anything. So the indicators are indicators. They're not like end all be alls. So we come here, we notice tension in the calves. We come down to the Achilles. You can either go one leg at a time, and you can go, okay, is it the calcaneus? Is it the ankle? No. I can tension into the knee. Is there an issue in the knee joint? If there is, we can address it a bunch of different ways to release tension in there. Is the tension in the SI joint, in the pelvis? Or we can even start to feel up more into the thoracics. So there's a spot right here. If you watch right here on the opposite side, you'll see it start to catch and move and flatten out right about here. Yeah. So I'm noticing a spot right here, and if I leave my hand here and pull on the Achilles here, I can feel this spot moving. Yeah, so they're connected. So again, it's something to notice. So start doing that and just notice, like, you might be able to just come here and be like, yeah, the left side is way more, it's not wanting to release tensionally at all. So then go explore the left SI joint. It can be that simple. And again, it's like, yeah. Yeah, it changes. Mm. So you might not use like you instead of reading through the heels, you might read through somewhere else. And that's where we can start introducing all kinds of shit. We can introduce cycle wiggle, where we're providing a wave throughout the system, noticing where it catches. Again, notice it's the exact same spot as we found before. This is literally where it stops moving. So somewhere in the kinetic chain, we're having issues. We can access that through so many. We're just putting movement in. Again, it's literally like this. Like you're putting movement in and noticing where in the chain. If this was the entire body, you're noticing where in the chain things are getting caught, where things aren't adapting. Because it should be fluid. Like we should be like fluid, but also maintaining tension. That's the whole point. So yeah, if there's an issue in the knee, then you're probably going to feel it in the knee. Like when you go here, you're probably going to feel it getting caught right in the knee. So yeah, another thing you can do is also mess with inversion and eversion. It's going to give you more of like rotation of the ilium in IN or EX. So what is it? It's like foot toes out is IN ilium. So you can play with that. Like, is it first of all, is 1 foot more? His are about the same. Is 1 foot more flared out? And then we can challenge. We can add flicks into the system and notice, is it traveling up? For him, it's literally all getting stuck in his mid-thoracics. But we can notice inversion and eversion of the ilium. Is an ilium stuck more in internal state? If so, with the heel isn't going to want to flick out. And that's another thing you can feel. Does that make sense? It's not that much, ass. All right. My mouth is dry, so let's get hands on.